Bell state measurement, and as a result of that, that entanglement will be lost and the qubit state will be transferred. That is one way, but only thing is it requires pre-shared entanglement, and that is also qubit, 2 qubits, and if you send that qubit also from one place to another, again attenuation and decoherence means loss of a state will happen. So how can we tackle that? Then we have something called entanglement stopping. So suppose that Bangalore is holding one entangled qubit with Hyderabad, and Hyderabad is holding one entanglement qubit with Nagpur. All we have to do is at Hyderabad, we will do a Bell state measurement, similar operation which we did for teleportation. And then these two entanglement will be lost, and Bangalore and Nagpur will be directly connected through entanglement. So that is the stopping part. So in that way, we can keep extending the range of entanglement. And finally, whenever you want to send a qubit state from one place to another, do the teleportation. One more method is where we can do hop-by-hop transmission. But hop-by-hop transmission, we already know that if distance is more, then the state will decohere or it may be lost. So in that case, what we can do is we can do the encoding, logical encoding. So for example, we have the repetition code in classical network where if I have to send 0, I will send 3 zeros. So even if one is lost, with the 2 I can conclude that this is finally 0 only. Okay? And similarly, one can be encoded with 111. That's the repetition code. But it has its own demerit. For example, if we flip 2 qubits, then we flip 2 bits, then we cannot recover. So we will encode it, and it will become another logical state. Then we will transmit it. Some loss will be there, and after that we have to do the recovery. After recovery, we will get the original state. Again, we will re-encode, and then again transmit. So this will keep going. Encode, transmit, recover. Encode, transmit, recover, and so on. Keep going. So this is one method. And there are several encoding techniques. For example, CSS is there, quantum parity code is there, repetition code I already talked about, and it requires sophisticated hardware for handling the error correction part. Now let's talk about computing nodes that we have available in quantum world. So one, we have monofunctional node. One of the example is CompNISC, which is noisy intermediate scale quantum. It can do only teleportation. So only one operation it can do. It doesn't have error correction capability, and I'm denoting one factor reliability. So it is like with what probability can it transmit a qubit. And similarly, the time taken in the transmission. Second one is a bifunctional node which is fault tolerant because it can do error encoding also apart from the usual teleportation. So it can do both. And similarly, I have here for this node also I have defined the reliability factor and the processing time. Now I am defining a probability of successfully transmitting a qubit from source to destination as R subscript SE. So it will be basically the multiplication of all the reliability factor of the intermediate nodes. So now coming on to problem statement. So I have a heterogeneous quantum network where I have monofunctional node, bifunctional node, and the associated parameter, and then we have a path on the network. So it may be a shortest path between a source and destination, and then I want to know that for this path, what choice of transmission mode will give me the highest reliability, the highest success probability that the qubit state will be transferred from the source to destination. So that is my problem statement. We are also constraining it by a time, because if time is more, the state will decohere anyway due to the environmental factors, for example, temperature, humidity. So some prelim approach that like I can only do teleportation because anyway monofunctional as well as bifunctional both support teleportation, so we'll stick to teleport only. There is no choice in that case. Second one is we can have brute force choice where for a n node, we can have 2 raised to the power n choices, and then check all the brute force approaches, and then find out which has the highest reliability. We have a greedy approach where we will simply select whichever has the highest reliability. We don't care about the time here. We simply select, he has better reliability, so take on teleportation, so take teleportation. If some node has better reliability on hop by hop, we'll take hop by hop. And then finally, we also have one dynamic approach where we will divide the problem into sub-problem and then try to solve it one by one. So for example, we'll start from the destination node, and we will use one memorization variable caching, which will store the node number and the time, and for that node and particular time combination, what is the highest reliability. So suppose we start with the destination node. So we are already at the destination. What is the time taken? 0. What is the reliability? But we are already at the destination. Then we will move on to the next node, E-1. Now E-1, how many choices are there? 2 choices. I can teleport, I can do hop by hop transmission. So out of that, which one is highest reliability? Take that one. And are we considering time? Yes. So we have a time constraint of t. So we'll see that if I choose suppose teleportation, then how much time will be left for the next node to do their operation, and so on. So this process we will repeat from end node till the source node, and ultimately at the source node level, we'll get the optimal reliability by checking the maximum of all the options. Complexity, if we talk about dynamic approach, we have n node, and our time, suppose that we have broken time into 1 units, so we have n into capital T. Spacer, so we'll take the same for that memorization variable. If I take brute force approach, so we have 2 raised to the power n choices, and for each choice I have to go through n nodes to calculate the end-to-end reliability. So that will be n into 2 raised to the power n, and the space will take only n for storing the combination at that point of time. Greedy is easy because we only have to go through n nodes and select whatever has the highest reliability, and it doesn't take any space. It's an in-place algorithm. So one of the example that I'm giving here is this, where, sorry. I think one slide is missing. So, here it was a demonstration of the greedy approach where we were checking that depending on what is the reliability and then what method we will select. And if we have continuous teleportation, for example, 4 nodes are continually doing teleportation, then we will do an entanglement swap first and then do the teleportation. Otherwise, we will simply do the loss tolerant encoding and send it to next node, which is like, and we'll do the recovery, encoding, and transmission again. So we tried on different hop count ranging from 5, 8, 10, 12, 15, and we saw that if we do not constrain the time, if we first let's talk about time constraint. So if we constrain the time, then greedy will be highest, because anyway greedy doesn't care about the time. But brute force and dynamic approach both will have higher reliability than the basic teleportation only. If we do not have any time constraint, then greedy, brute force and dynamic all will perform similar. They all will be the highest, and only the teleportation only approach will be always lower because there is no choice there. We also thought that can we do a clustering of the bifunctional nodes? Will that help in maximizing the reliability? So we did a clustering where we were clustering 4 bifunctional nodes together, then 5, then 4, then 3, 2, and we observed that when we have more clustering, so nodes in the cluster are more, then our reliability factor is increasing. So of course, because like if I use one teleportation only node, basically the monofunctional, and one bifunctional, then anyway I can only do teleportation. It's like language, if somebody knows one language, another one is two languages, still we have to talk in the first language only. So we conducted the experiment on heterogeneous node with multiple different capability, and we also check the clustering, which will help in deployment strategy, like where should we put the nodes in the networking, and we want to extend it to more heterogeneity. So for example, there is hop-to-hop teleportation only, that is also there. Then, based on this factor, reliability factor, can we have a routing algorithm? Yes. So we worked on that also, and it has been accepted in ComsNet 2025 workshop in quantum technology. And we also considered the fidelity factor. Fidelity factor is like if I am sending a qubit and its state changed to some other, then how much far is it from the original state? So the similarity factor between the intended state and the state that it got. So that also we have considered in our next paper, which has been selected at ComsNet. Thank you. Any question?
Thank you for this nice presentation. Any questions?
Anyway, my email is there. I am also here. If any question is there, we'll take up offline.
Okay, thank you. So let us proceed with the second talk titled A Cognitive Resource Aware Orchestration of Network Services for 5G and Beyond by Shameen Raj, Sai Bhavadish, Hemant Kumar and Garima Mishra from TCS.
Good afternoon. My name is Bhavadish. I am from TCS Research. Today I am here to present our paper, Cognitive Resource Aware Orchestration of Network Services for 5G and Beyond, on behalf of all the others, Shameen Raj, Sai Bhavadish, Hemant and Garima Mishra. So the following presentation is divided into these are the sections. Moving on to the introduction. CSPs, communication service providers, are facing several challenges with respect to seamless operations of different technologies like cloud computing or IoT applications or multi-access computing. And consumers also expect a zero-touch management in resolving the network issues. Adaptation of 5G is promising for CSPs in terms of low latency and high data rates as well as software-based approaches. So, anyways, however, the deployment of these particular technologies is quite challenging. So, hence we built our solution, cognitive resource aware orchestrator for handling smooth operations of network services. So, our solution delivers on-demand provisioning, optimal resource utilization, and it is managed by SDN and NFV. And it is also future ready for 6G networks, and it offers seamless management. There are multiple management orchestration solutions available, mainly focused on NFV solutions and our beneficial in small scale network deployment. So there is a need for high level orchestration solution which offers optimal resource utilization and also efficient operations of end-to-end network services. And some other focused on utilization of computer resources in 5G and nano without focus on end-to-end services, and some solutions on slice-aware VMs, VNF management in fog and cloud computing. And so there is a gap in end-to-end network services which offers dynamic slicing, QoS policy management, and also how do we mitigate the catastrophic event failures. This is our enough standardized architecture for SDN networks. So the operational activities in this communication networks are broadly classified into 3 planes: application plane, control plane, and data plane. So application plane comprises of SDN services applications along with the OSS or BSS layer, and there are self-service web portals for any service request. And coming to the control plane, it It is comprised of SDN layers and also network services like infrastructures like cloud computing, etc. Activities mainly focus on virtualization, coexistence, interoperability, and smooth function. And data plane comprises of several resources like UEs, RAN, core, and the infrastructure. So they are broadly classified into three resources: radio resources, network resources, and compute resources. So before moving into the teacher link, so there is a need for a new plane called management and orchestration plane in between the application and control plane. As you can see in the image, there is a orchestrator entity, customer services, and application orchestrator. So we propose our orchestration management orchestration solution, as you can see in the architecture diagram. So it comprises of three blocks: cluster managers and master orchestrators, and also slave orchestrators. So it is designed to be deployed as a group of clusters. So cluster contains two master orchestrators, one is primary and one is secondary, and multiple slave orchestrators, and is managed by the cluster managers. So the cluster's state and context information are gathered periodically by the masters, and it is stored for resolving any issues, any failures. So these are deployed as a microservices, and there is no tight coupling between the clusters and the respective cluster managers. So let's look more into the components. So there are total three components: master orchestrator, deployment, initial configuration, health and performance, and also the master interactions. This is the overall functional setup of the clusters. So initially, a set of cluster managers are deployed at different locations, and these cluster managers are responsible for deploying the clusters, including master orchestrators and also the slave orchestrators. So whenever a service request comes from the OSS or PSS layers, the master orchestrator takes the request and then deploys the respective worker orchestrators. It distributes the work into the different worker orchestrators. And first of all, if there is any problem, like any failure occurs, then in the master orchestrator, first of all, it's primary one. So the secondary one immediately starts up as there is a certain context exchange happening periodically, and meanwhile the cluster manager deploys one more orchestrator, master orchestrator, to keep things steady. And the SDN or NFV components are managed by the slave worker orchestrators. And this is the overall setup of our lab-based setup. It comprises of OA components like 5G UEs, RAN, core, and also SDN controllers like FlexRig, FlexRAN, hardware controllers, and ODA controllers. And it has FlowVisor, Networks Hypervisor, and open source manual. And it is managed by the Kubernetes cluster. So the wide network is emulated by using mainnet SDN networks to connect the core VNFs. And currently we are lacking infrastructure for large scale. So we are trying to deploy in cloud-based environments where the resource will be high. So we have validated our solution with 5G slicing. A set of requirements were given, as you can see in the diagram, there are 10 slices depicted. We can say 10 RAN slices and then 7 core slices. Couple of RAN slices are shared with one core slice like that. So here our focus was to validate the functionality of the solution and to troubleshoot, identify any errors or issues. So we have not considered the optimization of resources as of now, and we have tested with the higher scale also, deploying more slices, and we are currently working on increasing the scale of the functionality. So we conclude our work here. So we have summarized our approach on 5G service orchestration with the help of SDN and NFV networks, and we have demonstrated the AI-based initial setup, which is auto-deployed and configured. And we showcase the lifecycle management with NFV deployments and network slicing. We are working on validating other goals like optimal resource utilization, admission control, failure management, and dynamic slicing, QoS policy management, etc. And as part of the future work, we intend to build optimal RAN and core slicing algorithms and strengthen the orchestration mechanism, and also planning to validate the performance in large-scale deployments using different 5G test beds. So these These are the references. Yeah, thank you.
Thank you, Sai, for your nice presentation. Do we have any questions? Okay, no questions, then let's thank the speaker. Now we proceed with the final talk of today's session, titled Multi-Stream TSN Gate Control Scheduling in the Presence of Clock Synchronization by Avirup Ghosh, Carleton University, Thomas Kunz, also from Carleton University, and Saleh Yousufi from Udmia University in Ireland.
Hello everyone, my name is Avirup, and today I'm going to present my paper titled Multi-Stream Time-Sensitive Network Gate Control Scheduling in the Presence of Clock Synchronization. So Industry 4.0, or the fourth industrial revolution, applications would include telemedicine, industrial automation. These applications require deterministic, low latency, scalable, as well as reliable networks. So Ethernet is a communication medium which can meet these requirements pretty cost effectively. However, for Ethernet to be able to meet these, it must be augmented. So this augmentation of this next generation of Ethernet standards is being conducted by the IEEE Time-Sensitive Network Task Group, or IEEE TSN-TG. So basically, the time-sensitive network standards are classified into 4 different categories. So you have reliability, resource management, latency, as well as synchronization. And out of which we're looking at 2 particular standards, the IEEE 802.1 QBV time OS shaper standard and the IEEE 802.1 AS time synchronization standards, and how these 2 standards are interlinked. So to our knowledge, none of the previous studies focus on interlinking these 2 particular standards. Okay, so just to briefly explain the background. So what is TAS? So TAS is basically a shaping algorithm designed to handle periodic time-sensitive traffic. And it is used to providing deterministic end-to-end latencies as well as jitter. So what happens is that you have switches, and these switches are arranged based on predefined schedules at the egress port. So for example, we have switch 1, 2, and 3 here. And at each of the egress ports of these switches, you will have a schedule. So for example, over here, we have Q0 to Q7, with Q0 being reserved for time-sensitive streams. And at time instance T1, only the time-sensitive streams are allowed to transmit, while at T2 and T3 in switch 1, the others can transmit. Similarly, when the frames move to switch 2, at time instance T2, you can only have time-sensitive streams transmitting, while the others are completely cut off from transmission. And similarly, you move to switch 3, and you have this space bandwidth reserve at time interval T3. So for this, as you may have noticed, for TAS to work effectively, they need to maintain a specific standard time reference. So this time reference is performed by the IEEE 802.1 AS time synchronization standard. So the question then to begin is, why do devices need a constant time reference? Well, devices have a crystal oscillator which are subjected to various physical factors like pollution, noise, aging, etc., and because of this, they begin to drift. So even if devices are aligned, their timing references will change over time. So this sort of timing realignment is done based on a particular node known as the grandmaster, and the grandmaster, as you can see in this figure, it sends out periodic hop by hop time-sensitive signals to align all the switches in the network. But despite this, because of the clock drift, they will still begin to, the timings will begin to misalign. So you can see in the figure, the graph on the right, you can see that the time deviation between these devices are 0, but then just after synchronization, they begin to drift. And they begin to drift, and they keep drifting until they're resynchronized. And this periodically repeats itself. So basically, your drift can be either positive or negative, and it's usually measured in parts per million. And so, because of this drift, let's see what happens with TAS. So your TAS, as I said, they are predefined schedules. So you have a predefined schedule, for example, over here. So you have frame 1 and frame 2 being transmitted, which are time-sensitive frames. And they go from switch 1, they're adjusted based on your transmission, propagation, processing delays into switch 2, and then finally into switch 3. Now, this is perfect, and they're all aligned. However, if you have clock drift, you can see that suppose switch 2 has experienced this clock drift. You can see that its scheduling is skewed. Now, its scheduling changes. So frame 1, instead of when it arrives, it queues, and the queue accumulates, and as a result, when it goes to switch 3, it misses its cycle. So as a result, it hits the frame 2 cycle. So when frame 2 comes to switch 3, it again misaligns, and it can't transmit because frame 1 is transmitting at that particular period. As a result, the entire schedule is bust. So to counter this, what exactly do literature say? Like what do other studies say? So well, they say that one assumption is that there's perfect synchronization. So gate control, time-aware shaper scheduling is complicated as it is. So there's no point of doing this. So we'll assume that there is perfect synchronization, and we won't talk about clock drift and its impact. Or they consider a worst-case factor. So the worst-case factor essentially is you delay the scheduling until you're guaranteed that the frame arrives at that egress port. Okay, so the problem with either approach is, in the first approach, it's not practical for realistic network environments. In the second approach is that it introduces unnecessary delays, and it also causes variable jitter, which in turn impacts performance. Okay, so our paper contributions are such. So we say that whatever TA schedules you can form, you can use the network measurements from the time synchronization process to optimize your TAS schedules. So basically, you can use the clock drift information that you can derive based on the time synchronization process, and then you can use that to improve your TAS schedules. Our second contribution is that we propose an alternative scheduling mechanism, which says that we completely provide in this scheduling approach, we completely provide the minimal end-to-end delay possible, which is basically there are no queuing delays along the path, and this approach eliminates jitter. Our third contribution is that we introduce a quantifiable comparison, which assesses all these different scheduling methods. Okay. So before we discuss the scheduling methods, I'd like to elaborate on the two types of scheduling. So one is the delay-based scheduling, which is the literature-based scheduling, which states that you delay your scheduling until you're guaranteed that your time-sensitive frames have arrived at the egress port of the switch. The other is the adjustment-based approach, which was proposed by us in a previous paper, which says that you adjust your schedule such that as soon as your time-sensitive frame arrives at your port, at the egress port, it's scheduled immediately. So this approach results in no queuing delays and completely eliminates jitter. Based on this, we have devised 4 different scheduling methods, which we say that all these approaches can be optimized by leveraging the clock drift information obtained from this synchronization process. So these 4 different approaches is the worst case delay, the WCD, which is essentially based on the literature method. Then we have the network derived clock drift method, the NCD, which is an augmentation of the WCD and considers the network-derived clock drift measurements in the scheduling process. Then we have the worst case adjustment method, scheduling method, and then we also have the network-derived clock drift adjustment method, which enhances the WCA method by incorporating the network measurements for your gate control list, for your TA schedules. Okay, so so based on this, so we have these 4 different scheduling approaches. We developed this using an integer, solved these using an integer linear programming approach with the objective to minimize the end-to-end latency for all streams while meeting the deadline. So the basic challenge over here is that you have different streams which have different periodicities, and they all need to be aligned to a common network cycle, and they're all these schedules of all of them are interdependent. So the schedule on one switch will depend on the previous switch, which in turn will depend on the switches that preceded it. And so for that, we have a variety of constraints. So the list of constraints I've listed here in the slides, and they're covered in quite finer detail in the paper. So if you want to have a look at the mathematics behind this ILP approach as well as the constraints, I suggest you check out the paper. Okay, so we have a look at a simple example, where you have 2 switches and 3 different streams with periodicities of 100 microseconds, 150 microseconds, and 300 microseconds, which gives a network cycle of 300 microseconds, and how these are aligned, okay, in an egress port of a switch. So you have, for example, stream 1, which has 3 repetitions over the network cycle. You have stream 2 with 2 repetitions, and stream 3 with 1 repetition. So you need to align your gate control. You need to align your scheduling durations and offset it such that none of these frames, the scheduling durations, overlap with anything other, like any of the others. So for example, frame 3 should not overlap with frame 2 and any of its repeats, and in turn frame 2 should not overlap with frame 1 and any of its repeats, as well as frame 3. Okay? So finally, like in terms of our final contribution is to how do we assess these different scheduling approaches. We use a criteria-based method. So the criteria 1 is that the deadlines must be kept. So it's no good having a schedule that does not meet your timing deadlines. The second is we define what an infeasible solution is. So within a network cycle, if an egress port cannot fit your scheduling durations of all the streams that are going through that egress port, it's also no good. And then we also define a metric called the schedulability cost metric, which is essentially based on a factor of the scheduling durations across all the streams in the network. So this is covered in more detail in the paper, but basically the lower the schedulability cost, the more bandwidth efficient your schedule is. Okay, so then we come to the results section. We have 2 sets of results. One is based on case studies, and the other is more of a generalized study based on this topology, which we discussed previously. So here's our network parameters. We have a list of delays, propagation, processing, transmission. We have network parameters. Of this, it's important to note the minimum end-to-end latency of 39.628 microsecond. We also have the clock drift parameters, so we limit the range between -10 to +10 parts per million with a relative drift of 20 parts per million, and a synchronization of periodicity of 125 milliseconds, which gives the worst case error of 2.5 microseconds. So we developed our optimization program using CPLEX. As a post-processing phase, we use MATLAB. And finally, we use OMNET to display our simulation results. So in our results, we have 3 case studies. So you can see that each of these case studies have different sets of clock drifts associated with them, and we have the corresponding end-to-end latencies as well as the schedulability cost. So in case study 1, when we compare the WCD and the NCD, we see that the latency, that boundaries of NCD is lower than the WCD, whereas when we look at the WCA and NCA, we see that both of these schedules get the minimum end-to-end latency possible, which is what they're designed to do, but the NCA has a lower schedulability cost than the WCA. Moving on to case study 2, which is an extreme case because you have the clock drift extremities and they interleave. So it's plus 10, minus 10, plus 10, and minus 10. You see that the NCD provides lower end-to-end latencies, but at best the WCD can match the upper bound for the NCD. With WCA and NCA, when you look at the schedulability cost, you see that the NCA schedulability cost is lower. But now we look at case study 3, which is a very unique, which is a different case because you have your clock drift ranges are limited between -5 and +5 parts per million. And over here, you can clearly see that when you compare the WCD and NCD, you see that the end-to-end latencies for NCD is much lower than the WCD method, and when you compare the schedulability cost for the WCA and NCA, you see that the schedulability cost for the NCA is much lower than the WCA. So then we perform a generalized study, which is covered in more detail in the paper, and basically you vary the relative clock drift ranges and your synchronization periodicities, as well as you look at the extreme cases like in scenario 2 where you interleave the clock drifts. And when we compare the WCD and NCD, we see that the WCD tends to experience larger queuing delays, and in a worst case, it can result in an excess of 50 microseconds larger than the NCD. And when we compare the WCA and NCA, we see that the NCA has lower schedulability costs and has a wider range of schedulable regions. As you can see in the white spaces for the WCA, white spaces means that those regions aren't schedulable, whereas in the NCA you can see that the heat map shows that there are more colors, which means that those regions are schedulable. So in conclusion, basically we have said that clock drift considerations are important when you're doing TA scheduling for time-sensitive networks. We presented 2 scheduling approaches, a delay-based approach, which is better in terms of bandwidth consumption, but it has its limitations in terms of accumulative delays. And you also have the adjustment-based approach, which is better in terms of managing latency and jitter, but is also bandwidth heavy, consumes more bandwidth. So, however, both these approaches can be augmented using network-derived clock drift measurements. So the scheduling, that's what the NCD and NCA approaches were. So as a future work, basically we had a simplified topology in this paper, but as a future work, we are actually working on expanding this topology, as you can see in the figure here, where you have many more multiple streams, multiple different switches and more devices. And we're going to we're going to automatically generate these scripts, and this should be an open source tool that we expect sometime this year, so that anyone in this audience can generate their TA schedules based on their preferred method, as well as check what it looks like based on network measurements from OMNET. So that is our future work. And thank you for your time, and are there any questions?
Thank you, Aviru, for such a nice presentation. Do we have any questions?
You gave that example with 100, 150, 300. What if you had like 90, 160, and 290 when you did the LCM computation?
90, 160, and
290.
That you technically could, but then your LCM would be really large, and you would have many more repetitions. You could technically do that, but it would would be challenging.
Or is there a way to work around that?
That is a good question in terms of like if your LCM is really large and you have many repetitions, so how does the gate controllers like how do your TA schedules work? So that's something we have been thinking of, but we don't have any answer yet for that.
Yes.
Any more questions? Okay, let's thank the speaker then. With this, we conclude session 3. Okay, so now we have poster demo and THD symposium in the corridor. We can proceed for that. Otherwise, we have tutorial 2 going on in seminar 2. And tutorial 3 is going to happen here in auditorium 1.
Hello. Yeah. Okay. Hello. Okay. Hello. Testing. Hello. This is off, right? This one. Hello. Okay. You put on in there. This is always on. Hello. Hello. How is it now? Now also. Hello. Hello. How is it now? No? Double voice. Hello. Okay.
Enakra.
Let's start. Okay. So, yeah, good afternoon, one and all. So today we have this tutorial 3, which is basically titled as ORIDE, where we are talking about Open RAN innovation and deployment exploration. So this is joined with Dr. Koteshwara from IIT Dharwad and Dr. Venkateshwarlu, who recently joined as a postdoc at UT Dallas. So this is the outline of the presentation. So I will take the part 1 where I will talk about the evolution of the mobile networks and then spend how ORAN framework is trying to change how operators are going to deploy the cellular networks of late. So that is the part 1. Then Dr. Koteshwara is going to talk about the demonstration of the Open RAN. So there is a hands-on kind of session. So we will see how we can use various open source tools to be able to emulate functional ORAN system and some use cases how ORAN going to do that, followed by Q&A session. So, okay, so some motivation. I think yesterday we had Professor Kiran Kuchi and Dr. Dilip talking about 6G and other things. So motivation is the same. So the number of devices that are being connected to the internet are kind of exploding, the number of devices. This particular illustration talks about various kind of devices that are connected. Some statistics from Cisco. As you see here, we are touching almost, or maybe crossed already 30 billion devices. But one question to all of you is, how many of people are currently connected to the internet? So do you know how many humans are currently using the internet? Do you know what is the current statistic? It is around 9 billion. So that way, the number of devices are much more than number of humans. That is going to increase quite significantly as internet is getting adopted in different markets, and also people are having more and more personal devices and also IoT devices. That is one statistic. The second one is about the data explosion. As startups and internet companies come up with more and more over-the-air applications, as you see, the demand for data increasing quite significantly. What you see in this picture is from Ericsson Mobility Report 2020, which basically showing about how much data is consumed per month in exabytes, which is basically 10 to the power of 18 bytes in that particular order we are talking about. As you see here, there is a lot of data, and if you look at which applications are the ones that are kind of consuming a lot of data, it is the video, all kind of videos, whether it's streaming or online kind of gaming, and all these kind of things are consuming lots and lots of video. Video is the one that eats the entire pipe that operators are having. So then comes, as I said, before talking about the ORAN, I will talk about some evolution of wireless networks. In wireless networks, we have various kind of networks. One category of the networks that we call here are the access networks. By name access network, this is the medium, or this is the platform using which end users, if you look at in this picture, different end users, how they are connected to the internet. In this case, when you say that connected to the internet, it is a gateway router that is there. So access networks are the networks which basically provide you an infrastructure which helps you to connect to the nearest gateway router to the internet. So we have both wired access network and wireless access network. Because in wireless access networks we use radio waves, we call them as radio access network. That's where the term RAN comes into the picture. So what you see on the left-hand side is the local area networks like Wi-Fi, which offers various kind of speeds over the generations, but mostly used for indoor settings. But then we have these wide area wireless access networks. As you see in the picture, these are the ones that provide you untethered mobility to the user, so that we can access data no matter wherever you go, and including the satellite, so that we can connect the unconnected and whatnot. When it comes to the wide area networks, we call them as mobile networks or cellular networks. And there's a generations of cellular networks. Currently we are at the generation 5, which is offering up to hundreds of megabits per user. I'm talking about per user average data rates. So what you see is a kind of snapshot of the evolution of these radio access networks. On the left hand side, what you see are the cellular networks. So all the way from 2G to 5G, and also 6G is also being projected here. These are the kind of cellular networks which are like mobile networks. Right hand side, what you are seeing are the kind of local area networks and even the metropolitan area networks, which also provide you wireless coverage but limited wireless coverage. As you see, different kind of radio access networks depending on the kind of speeds and coverage that you are going to get. So we look at the evolution. So this particular slide is showing you how the cellular networks are evolving and how the people have started using different kind of technologies for voice, data, SMS. We started with circuit switching in the first generation, and also even in the second generation, which is the GSM, which came in 1990s. It used to have only circuit switching for voice. And then we have, as you see here, circuit switch data is also added into the GSM at a later part in the time, even before the 3G comes into the picture. So then we have 3G. 3G is basically meant to provide not only the voice but also the data. But as you see in the picture, voice is still being used on the circuit switching. For data, we can use the packet switching. But when it comes to the 4G, which is called IMT Advanced by ITU, where we are using packet switching for both voice and data. So, thanks to the way internet has evolved and the benefits of packet switching, even for kind of things that we historically used to do using circuit switching like voice and video conferencing, we started using packet switching with kind of increasing the network capacity and doing caching and other intelligent techniques. So this is the kind of overall evolution up to the 5G. So this slide is showing the same thing, which basically showing you for voice what you are using, for SMS which technology you are using, for data which one you are using. So as you see here in the 4G, which is all digital, and we are using packet switching for all the things, including SMS too. Okay, and also the speeds are also increasing, and as you see here, the data rates are going up to the gigabits per second. But these data rates are kind of a peak data rates. If you are the only one user with very good channel conditions, you can enjoy this. But if there are many users, operator want to share this data across the users. Let's look at this particular tutorial is more about the radio architectures, how these architectures have been changing in the context of how operators are deploying these networks. So let's spend some time looking at the evolution of these cellular network architectures. So let's start with 2G. So in the 2G systems, we have something called base station system, BTS. These are the cell towers that you see outside. And these BTS are connected to something called base station controller. As you see, a base station controller can control multiple towers together. Together, all these are called base station subsystem. So then what you see here is the base station controller is connected with mobile switching center. It is similar to the way in plain old telephone systems, like operators like BSNL have their own switching center. It is like a mobile switching center which kind of let people talk with each other. And one other thing that you can notice here is mobile switching center not only connect with other operator switching center, it also connect with plain old telephone system, public switch telephone networks, so that even the landline users also can connect and reach to the mobile users. That's the idea that you can see it here. So then look at what has happened from 2G to 3G. So in the 3G era, there's a renaming has happened. BTS has been renamed as Node B, and BSC has been renamed as Radio Network Controller. But otherwise, as you see, the functionality wise, they kind of do the same thing. Okay, whether it is a 2G or 3G, except that over the year we are using CDMA and wideband CDMA in the case of 3G. But architecture wise, it looks very similar terms of the infrastructure. But unlike 2G, later in the 2.5G as well, we wanted to provide data services so that people not only can able to send SMS and talk with each other, they can also send emails and connect to the internet and other things. So how do you provide internet connectivity? Not only you want to reach to the public switch telephony systems, you also want to reach from the mobile networks, also the data networks. And the popular example of data network is the internet. So that the mobile users can also reach to the internet and avail all the internet services. In 2.5G, that is called GPRS, and later it has become Edge. These are the technologies where they added two control nodes called serving gateway support node and GGSN. This is also another node. Basically, one of them will act like the gateway, other one will act like kind of a forwarder. So using which we can able to these are more like a routers in the context of internet architecture. So that way it is more like a gateway router for this particular operator's network, using which this operator can connect all its users to the internet. So that way internet services can be available by the user. So this is a 3G architecture. Now look at how the architecture is evolved from 3G to the 4G, where as you can see, since it is an evolution, they named it as evolved node B. Node B has become E node B. So this is the one that is at the cell side. So unlike base station controller and radio network controllers, which are kind of managing multiple cell sites, there is no such thing in the case of 4G and later in the 5G. Reason being, as you have more and more active components in the network, it becomes more and more challenging for the operators to manage the equipment. Passive equipments are okay. If you lay the fiber, it can run for 10 years or 20 years or 30 years, except there are a few fiber cuts here and there. But active components, every 3 years, 5 years, you have to upgrade or replace. That is, there is a lot of capex in terms of the infrastructure that you have to invest in, and also the maintenance of all these active components. So, in order to reduce the operational expenses to the operators and also the capital expenditure to the operators, what the 3GPP has decided is, it wanted to reduce the number of active components in the path from users to the internet services. That's the reason why these kind of RNC and Node B kind of merged together into one entity called eNode B. So that way, eNode B is more powerful compared to Node B and BTS that you see in 3G and 2G era. And then it comes to the core network. As you see in the core network, we had mobile switching controller, MSC. Then we have GGSN and SGSN in the case of 3G. And when it comes to the 4G, you can see similar entities, but now we have more and more components, packet gateways, serving gateway, the multi-management entity, which are all together called something called evolved packet core. So that it is a kind of the 4G core that we got in the case of 4G. So this is the evolution from 2G to 4G. Now I will show you what is the network architecture in the case of 5G, which looks very similar to what has been done in the case of 4G. So it shows an example of 3 cell towers, which is kind of providing coverage to multiple users. So very often what happens is these cell towers have the backhauling to the mobile core or the 5G core in this particular example, using a fiber optical network. So basically it is an optical transport network. In fact, this itself is another network using GPON and other technologies that people use it. But we are kind of assuming that there is a kind of a connection that using which cell towers can connect to the mobile core. Because this technology is not part of the 5G, but we need a mechanism using which you can connect cell site to the mobile core using the backhaul link. That's why we call that as a backhaul network here. So that way we have a backhaul network which is connecting the base stations to the mobile core. And the collection of base stations together, we call this as a RAN. Okay? Including the mobile core, we call it as a mobile network or the cellular networks. And in the mobile core, I will show you the following slide. We have gateway router and other entities using which we can do the registration, authentication, and provide the internet services. Okay? slide is showing the same thing. The difference between this illustration and the following is, if you zoom in into the mobile core and see what is inside, is what you can see it here. So at the bottom what you see is that, okay, I forgot to mention, UE stands for user equipment, all the mobile devices which connect to the 5G networks or even the 4G networks. We use the technical term called UE, user equipment. So then we have RAN, the radio access network, the collection of the base stations. And when it comes to the 5G core or the mobile core, so it contains all these functional elements. There are lots of entities, and finally we have this UPF, which is there in the data plane, which is nothing but the router which is connecting the cellular network to the data networks like internet. So in the 5G core, we have only one data plane entity called UPF, using which you can get internet access or the data access to, even for enterprise or private wide area networks. When it comes to control plane, as you see, there are tons of entities. You can see there are lots of acronyms and the meaning of that. I'm not going too deep into that, but if you look at some of the things that are important here, like there's something called network slicing in 5G, where operators can logically create multiple networks on the same physical network. It's more like a virtualization that we do in the cloud computing, so that we can create virtual machines and allocate to the different users. Similarly, we can do multiple logical networks on the same physical network. To support that, we have the network slice selection function. There's something called policy and control function, which basically talks about are you prepaid or postpaid or what is your tariff. All those kind of things are being controlled there. So then we have authentication function and service management function, access and mobility management function, which is a kind of a MME that is there in the 4G, which has been split into these two entities. That way authentication is separated from this thing. So those who know software-defined networking, what has been done here in the case of 5G is all the advances that has happened in cloud computing and also in the case of software-defined networking has been nicely embraced by 5G in this particular architecture. That way you can see a clean separation of data plane and control plane. In the data plane only we have UPF, then we have a lot of entities in the control plane of the 5G core. Not only that, you can see there are lots of the interfaces which are kind of integrating all this each other using something called service-based architecture. So what is the meaning of this service-based architecture is, whatever the advances that have happened in the internet in terms of how HTTP has kind of ruled in the entire internet in providing what kind of service that you want, similar HTTP-based interfaces, stateless architecture that you can use even in the case of 5G, so that people who are good at developing internet technologies can also come and do the development for the 5G, so that number of qualified service engineers or the experienced engineer or the developers who are available for 5G development can be the same as those who are currently working on the internet technology. That's the idea behind embracing the recent advances in the internet. So here what you see is the 5G protocol stacks. Unlike internet, where we have only one protocol stack, which is the TCP/IP that we use it, but in the 5G we have tons of protocol stacks. There are lots of protocol stacks. The way to understand this picture is, okay, this illustration what you see is the user plane. That means when you are sending the user data, let's say you are kind of sending an email from your mobile device to your friend who is connected to the data network like internet. So when you want to do that kind of thing, user equipment has to be connected to the base station, that is the G node B, and G node B has to forward the data to the user plane function, which is nothing but the router. Sometimes what happens is, as you see, any network contains a collection of routers and switches. Only one of them we designate as the gateway, which is the one that is connected to the ISP's counterpart on the internet in the autonomous system. So that is the called a PDF session anchor. So this is the one which assigns the IP address for you and does the routing for your purpose. So as you see, if you look at in the picture, the user is connected to the base station, and we have a kind of protocol stack here. So if you look at any protocol stack, it could be like 5 layers or 7 layers you can define. But what is important to note down here is on the user side we have yes the physical layer, that is L1. Then we have layer 2, which is further divided into 4 different components: MAC layer, radio link control layer, PDCP layer. Then we have this service data adoption layer. These 4 layers together comprises your layer 2. Like in the internet, or when you look at Ethernet or the Wi-Fi, there we talk about LLC and MAC. So here, LLC and MAC are further decomposed into 4 different entities depending on the functionality that they have to do it. So when it comes to the base station, because it also not only has to talk with the user, it also has to talk with UPF and other entities. It needs to have dual stack or multi-stack. So depending on how many entities, what kind of protocol that he has to talk. So that way, the architecture is quite different and complex compared to the architecture that you see in the case of internet. So internet architecture is simple, and maybe that is the simplicity, that is the reason why internet has become so popular. But having said that, increasingly, when you look at the GSM, which is a 2G compared to the 3G and 4G and 5G, things are becoming more and more open, standardized, so that it is easy for us to understand and also contribute actively to the thing. So this is the case of user equipment talk with the base station and UPF and other things. So lots of things happens here, and this is talking about how 2 base stations will talk with each other. This is in the context of handovers. So here what you see is another bunch of protocol stacks. This is in the case of control plane. So what I mean by control plane is when let's say the user is connected to the network and want to do the registration procedure, or when the user is moving from one base station coverage to the other base station. In that case, base stations and user equipment has to exchange certain set of control messages. For exchanging control messages, you may not have to use the same kind of protocol stack that we have to use in the case of exchanging the user data. But in the internet, we do the same thing, more or less. But in the case of cellular networks, because of the complexity and the entities that are involved, there are separate protocol stacks with separate entities that are defined here. They look more or less same, except that in the case of control plane, we have something called RRC layer. RRC here stands for Radio Resource Control. It does lots of things, including checking the channel quality and seeing that the user is connected to the base station with better quality and other things. So this is in the case of 2 base stations doing the handover. So first they talk over the control plane to decide to the handover. Once the handover is successful, whatever the pending data that is there in the old base station will be forwarded using XMU interface to the other base station. That's what you can see it here. Okay, so now I will show you how operators are typically deploying these cellular networks and what is the kind of evolution of in the actual deployment. So far what you have seen is what is RAN and how the RAN has been evolved from 2G to 4G to the 5G, and what are all the different entities that are present in this RAN, like we have these BTS, base station controller, eNodeBs and other things. Now what we look at is the actual deployment and what is the evolution that has happened there. This is a typical cell site that you see it outdoors wherever you go. So what you see on the top are the antennas and the radio heads. And so when you talk about the base station, so this is an example of a monolithic base station. What I mean by monolithic base station? The entire protocol stack is sitting at the cell site. So this box that you see it here, inside all the layers of the base station, like if you go back to this illustration. So this is the base station protocol stack. So on one side it talks with all the mobile users, other side base station will talk with UPF over the backhaul link. So that is there is something called NR-UU interface, with using which it talks to the user, with using N3 interface which talks with the UPF. So interface, the term interface may look a bit confusing. We use the word interface or network interface card for the interface that is connected with your computers or the radio in general. But here the interface is more than that. By by saying there is an entry interface between the base station and the UPO, basically we are talking about there is a protocol stack, entire protocol. Of course, lot of entities of the protocol stack may be the same or used across different interfaces, but the point is here we are using the GTPU protocol at the higher layer, which is running on top of UDP protocol. So that's what you see here. Similarly, there is an NI interface and NR interface, XN interface, N4 interface. Yeah. So as you see here, if you compare XNU and N4U, everything is same except the top layer. So if you look at these two architectures, all the layers, bottom layers, 1 to 4 layers have the same stack at both the stations, except that here we have GTPU, here also we are using the GTPU. Depending on what base station you want to send, what is carried into the GTPU changes. So, but to avoid any confusion, they kind of name it as different interfaces. But otherwise, many of these interfaces do a lot of similar functionalities using very standard protocols like TCP, UDP, SCTP, and other things. Okay, so this is what I'm showing an example of a monolithic base station. This is also another picture that is showing how you typically see. Sometimes what you see is outdoor, these cell towers are neutral. That means these are the third-party companies which house these radio heads of multiple operators like Airtel, Jio, BSNL, so that they can save some cost of renting and diesel and other things. Okay. Let's look at the typical deployment. I was showing that previous picture. It is a monolithic deployment. Like this is the physical system, but if you look at the block diagram and see what is actually composed of. So at the cell site, on the top of the tower, we have these antenna elements and radio heads. We call them as remote radio head. Then there is something called a front hall interface. In this example, we are using CPRI, which is a proprietary interface, using which the IQ samples come all the way from remote radio head to the baseband unit. So baseband unit is the one that actually implements your layer 1 and layer 2. Okay, and it is up to the operators to decide how much to implement at RRH and BBU. I will talk about in the following slides. But in general, in one simple implementation, you can assume it is your radio part, which is RF front end. Then we have this BBU, which implements most of the L1 and L2 stack. So base station doesn't have L3, it doesn't really understand the IP and other things, even though other side when it talks with the mobile core, it talks with that. So then the base station has to forward the data or the receive the data from the internet or from other operators network. For that we use the backhaul link. So what you see is an example of there is a small animation here. Basically what this picture is also trying to show is, this is a legacy monolithic deployment where a typical operator procures all these components from a one vendor. In this example we are showing like Nokia, which is a vendor for base stations, where you go and get all these components and deploy it to your cell site for offering the services. Okay, but one thing that is happening from 2G to 4G to 5G in order to provide better coverage and also support higher data rates to meet these bandwidth hungry applications is dense deployment of the base stations. We have to deploy more and more base stations. That's why we get the frequency reuse. Yes, by deploying more base stations, we can reduce the frequency, we can offer more capacity, but it is extra capex and opex to the operators. How to ensure that in order to meet this bandwidth crunch and meet the data requirements, operators don't end up burning their pockets and not getting any return on the investment. So that's where the rest of the talk is going to talk about. What are the innovations that operators community was doing in order to reduce their cost while upgrading the network from 3G to 4G, 5G to 4G to 5G, tomorrow 5G to 6G. There are different solutions. So that's where the RAN evolution comes into the picture. So look at in this picture how the RAN deployment is being done. Here what I am showing is not specific to any specific generation of the cellular networks, like 3G, 4G or 5G. But predominantly what I'm showing here has happened, started with the 4G, it is currently also being practiced in the 5G. Later it could also expected to happen in the case of 6G too. So this is what I mean by legacy or the monolithic base station, where at the cell side, operators will have all the components deployed. Like this is the cell side, where the operator has to deploy everything. Then there is a backhaul link using which the data from the base station is forwarded to the packet core. So this is also called decentralized RAN. It is like a distributed, at all the cell sites we have monolithic base stations that are deployed. That's how all of us have seen 2G, 3G networks and even most of the 4G networks actually got deployed. Then there is an evolution, companies like China Mobile, which is equivalent of BSNL in India, like that is a national player. They have lakhs and lakhs of base stations. They feel that it is becoming too expensive to deploy and maintain all these base stations. What can we do without actually changing the standard? So that's where came something called central RAN. The idea behind the central RAN is, as you see in the picture, rather than deploying the BBU at each cell site individually, aggregate them at a central office. It is simply aggregating. Rather than putting in each and every room, take all the boxes and put in one room. Advantage that you get is common cooling. Rather than putting 3 ACs, if you have 3 rooms, if you put all of them in one room, you can reduce the cost and even the manpower cost and other things. That's where the central RAN. So it is simply putting the boxes from distributed cell site to the central location. That is the CRAN. People confuse CRAN with also Cloud RAN, but the Cloud RAN comes to the picture here, but otherwise ESC stands for central RAN, so centralization benefit. So then came the concept of virtual RAN, which is also called Cloud RAN. The idea behind the difference between these two here is, once you put the things in a central office, we can also try to bring the virtualization thanks to the cloud computing advances, so that I can deploy like OpenStack or any Docker or container kind of technologies and put all these BBUs as software instances running in the general purpose hardware. The way here, unlike the hardware that you see it here, hardware that we are using here is the general purpose, like the commercial off-the-shelf servers from Intel, ARM and other things that you can use it here. So that way one is because they are using a general purpose hardware which is sold in millions and billions of devices, the cost of each hardware is lower, and thanks to the cloud computing we can able to make lots of virtual instances on the same hardware, even though there are some issues during the peak times that you may face it here. So that is the virtual RAN. And so that way, this is the virtual RAN. Then comes disaggregated RAN. If you compare this illustration with this illustration, the difference being, what I'm showing here is the BBU, that is the L1 and L2. So what has been done in the case of disaggregated RAN is, disaggregation is decomposing into multiple smaller components. So here, BBU has been decomposed into multiple logical components. In this example, what we are showing is the virtual central unit. In this case, it is a physical distributed unit, but we can also have virtual distributed. Basically, BBU is divided into CU and DU. And because now they are split into 2 components, then we need to have one more interface between these two, which is called mid-hall. Earlier we had only back hall and front hall. Now to connect CU and DU, we need to have something called mid-hall. So this is also another interface that has to come into the picture. So that way what we are doing is the disaggregation. Then came the Open RAN or ORAN that you see it on the right hand side. So if you look at in terms of the picture, it also has the DUs like what you see in the disaggregated RAN, and it also has the CUs like what you see in the case of disaggregated RAN. But in the Open RAN, there are 2 main things that have happened. One is, as you see in the picture, there is something called RAN Intelligent Controller. How we can bring AML techniques to be able to the RAN optimization. So can we the big data that is inherently there in the cellular systems to be able to better network automation and control. For that, the ORAN framework talks about using something called RAN intelligent controller. That is one thing. And other major thing, as you see here, the term, the keyword open. What is open here? The interfaces that are there here, the front hall interface, mid hall interface, the back hall interface are open. Those who know internet technologies, you may look what is open, what is closed, but because in the internet everything is open. IETF makes the standards, and these standards are open for anybody to read, comment, and implement and other. Same thing has been done in the case of cellular networks by ORAN Alliance. That's where the keyword open comes to the picture. Otherwise, disaggregated VRAN and open RAN are exactly the same, except that in the case of disaggregated RAN, even though, as you see here, I divided into DU, CU components, I can still use my proprietary interfaces to connect all of them. That means, if let's say take an example of vendors like Ericsson and Nokia, they can also sell you legacy RAN, centralized RAN, VRAN. They can also sell you disaggregated RAN, because these interfaces that you see here, back hall, front hall, and the mid hall, they are not standardized by 3GPP as part of 5G standardization or the 4G standardization. Operators felt that there is a need to standardize and make them open. So that's what happened, done by Open RAN Alliance, which is comprises of mobile operators, academicians, researchers, and vendors like Ericsson and Nokia. The beauty of the Open RAN, which I will also talk about in the following slide, is we can do mix and match. Up to these 4 generations of the cellular systems are RAN architectures. These components are kind of interconnected with each other using proprietary interfaces. There is no guarantee that you can do mix and match. But with Open RAN, being open standards, I can buy different components from different vendors. They should be able to interoperate with each other because they're all speaking the same language using the same interface. So same thing is being shown in this picture. I don't want to repeat again, but otherwise what you see, unlike in the previous picture, is 2 important points. Historically, because we are using the dedicated hardware and also software, the systems are highly reliable and also damn expensive. But when it comes to the VRAN, disaggregated RAN and ORAN, we are using the card servers, which are damn cheap, but they may not be highly reliable. So that way we are kind of reducing the cost, but at the cost of reliability and fault tolerance into the system. How do we achieve that? So if you look at today, when you use any cloud computing platform like Azure or AWS, they also run on the same cards hardware. But whenever you use this kind of cloud services, majority of the time or the most of the time you see them working flawlessly. But behind the scene, there are lots of components that get failed, links get broken, and hard disk getting crashed and other things. But you don't see, thanks to software-defined networking. Behind the scene, they try to make sure that end users should not feel any pinch of some other component getting failed by throwing more and more hardware, adding a lot of redundancy in the hardware that you do it here. So can we do the same thing that data centers have been upgraded into the cloud data centers by these cloud companies? Can the mobile operator do the same thing? That's the idea behind this ORAN concept. So what you see here is the even more complex picture. So maybe quickly try to explain here. So what I'm showing are the functional splits. So okay, here I'm showing horizontally. What you see here is the base station, which is basically the protocol stack of the base station. Like as I was showing earlier, we have the RF, then we have the physical layer, MAC layer, radio link layer, PDCP layer, RRC layer, HDAP layer, and other. These are the various layers. So when you are doing a disaggregation, where you are dividing the base station into multiple smaller components, where do you want to do the split in the protocol stack at the L1 and L2? So as you see here, there are 8 different options defined. That means, take one extreme example of option 8. What option 8 basically talks about is, at the cell site only I deploy RF, rest of the components I deploy in a remote data center or in a remote edge cloud. That's the idea behind option 8. But if you go to other extreme option, option 1, where it basically says that only RRC is deployed in a virtual platform, whereas the rest of the protocol stack is deployed at the cell site. Depending on which option that you choose, there are lots of trade-offs in terms of the bandwidth that you require and the cost of the hardware that you have to deploy at the cell site. For example, at the cell site, if I do option 8, because it is just RF, which is very dumb in nature, there are no active components, the cost of the cell site comes down quite drastically. But all IQ samples have to forward all the way from the cell site to the central office. That way I invest more on the front hall bandwidth. Okay? And also depending on the quality of the links, there is a chance that your radio links may get failed also. So we have to factor in these reliability related challenges. So that way there are lots of trade-offs as you go across these different options. So as you see, there are lots of options, there are lots of trade-offs involved. Which option is better? So after spending good amount of the time, the community felt that too many options are also not good. Let's go with a smaller subset. The one that ORAN that currently is using is this particular option. So the one that you see on the rightmost, at the cell site you deployed RF and the most complex, the lower physical layer. Then higher part of the physical layer, MAC layer, RLC you do as a distributed unit. And then using the F1 interface, which is the one that is the mid-hall interface, you connect DU to the CU where you have the PDCP, RRC and LDAP layer. Then the central unit is connected to the 5G core, mobile core. So this is the one, when I was talking about the ORAN architecture, we are kind of using. But having said that, one can use any of them, depending on maybe in one region of the world if the diesel is free or the fiber is free, then you can try to design your system entirely different way. But all these options exist with open and standard interfaces. So this is an example of legacy RAN. So what you see is the entire base station of Ericsson is kept it here. As you see, this is how I said it, at the base of the cell site, what you see is the BBU. If you open the box, inside what you see is this one. It looks like any server in the data center, except that it is a carrier grade with lots of capacity and lots of reliability built in. But what you see on the right hand side is a disaggregated RAN, where we are kind of dividing base station into DU and CU. Even though in this example it is disaggregated, they are actually kept at the same cell, same location. So disaggregated, but today also in the demo you see, we do the disaggregation and we have DU, CU, the core, everything is in one computer. So we can take, or you can split across the group. So depending on the latencies and the kind of guarantees that you want to expect from the system. This is an example of dish wireless system that they have deployed in US. So what is the benefit that you get with disaggregated networks? There are lots of advantages. As I was just mentioning, we are using the general purpose hardware, which is a kind of reduces the capex. And also we are doing centralization. That means we have a common central office where you can put all the entities and manage with one pooling system, one UPS, one net system network administrator. We can be able to save even the operating expenses as well. And also, those who know about cloud computing talk about scaling, horizontal scaling and vertical scaling. So depending on the load, you can power up more servers in the data centers or you can reduce so that your running bill can be reduced. Or like the example of Amazon, how they decided to use the spare servers for AWS services because their e-commerce business is not using all of the servers. It is hardly 10 to 15%. They decided to sell the CPU cycles or the rent the CPU cycles that became the AWS. That's what the cloud computing is about. Here also, operators, when they deploy this carrier grade telco cloud, they don't see during the midnight if there is not much traffic. but still you have the CPU cores available. Then you can do some kind of ML training, or you can do some edge computing, or you can do some caching. So that way, there are lots of things that operator can repurpose the hardware during the times when demand from the cellular users is less. But when the demand increases, they can scale up. That way, we can do both the horizontal or the vertical scaling. So maybe next 10 minutes, I will try to wind up on this introduction. I already given enough material about what is Open RAN or ORAN. So some more internal details. So as I said, it is a consortium of operators. It is driven by the operators. Then even the vendors. Initially they were quite reluctant because as a vendor I wanted to sell my entire solution to an operator. I don't want other operators also start putting their own boxes into the same deployment. But having said that, there is a lot of players in the system and things are kind of maturing. So you can see city like Hyderabad, we can have one central location where we can put all the city. So that kind of thing that you can see. Which operators felt there is a need to add it. That's what the ORAN Alliance from operator side especially brought into this ORAN architecture. And at the bottom what you see is the O cloud. What the meaning of O cloud here is, all these components that you see here, whether it is RU, DU or CU or the near RTLC or non-RTLC, except the RF for which we need antennas which has to be physical in the nature. All rest of the things can be deployed as software instances on a cloud. That is called O cloud. That way, this O cloud is the one that using which we can deploy all these components. Okay, and yeah, I think yeah. So this is at a very high level. If you go zoom inside this architecture, what each component does, especially in the context of the RIC. RIC is the one, as I was mentioning, the major innovation here from the ORAN Alliance. So if you look at what happens here is, among all the interfaces that you see here, we have something called E2 interface, which connects all these control units and also, as you see here, the blue line, the distributed unit, to this near RTLC, where we have something called radio network and information base. Basically, you collect all the network data, all the L1 data, L2 data and other things, have all the data, the big data at one location, and use this data because as you see, we are collecting at the network level. If the operator in a city has 500 to 1000 base stations, you have all the network data, how the base stations are functioning and where the radio links are failing. All the data you are getting in a central database. Once you have that, we have a global view of the network. We can do a lot of interesting things which were not possible earlier. Because earlier in disaggregated or monolithic LAN, each cell site, the base station is knowing, but it is not sharing with anybody else. Here, we are kind of telling the story of what is happening. That can be quite effectively done if you have all the information in a central place. So that is what the near-arteric does. Things that you want to do at the ground level of less than 1 second can be done using the near-arteric. So then we have, as I was mentioning, operators have a lot of things to worry about. One is whether the server is facing any memory leaks or whether it is facing any link failures. All that kind of other information also that operator wanted to collect. That can be done using called orchestration and automation. So there you can maintain the inventory, you can decide the policies, you can push the configuration to all the base stations. Rather than configuring each base station separately, you can do over the air or over the network updates to all the base stations. That's what you can see. And NFVI is a platform, as I was mentioning, we can use that COTS hardware and apply all the advances in Kubernetes, Dockers, OpenStack to be able to virtualize all our components. I think this is a kind of repetition of what I was saying earlier, but as you see, yes, at the top what I have is the SMO, that is the non-arteric. So, okay. So, AML, I think yesterday talks were also talking about keynotes on AML. You can apply AML at any layer in the protocol stack, all the way from the physical layer to the application layers. But here what we are talking about is, can we do the network management, network optimization using AML? So that's where we can use the non-arteric, that is a part of service management and orchestration. So for orchestrating these network entities, like by creating these virtual machines, containers and other things, and also checking the health of them and kind of troubleshooting, can I use AML? So many times what you do is you use the near-arteric to be able to train the models and use this A1 interface to push the train model to the near-arteric for the inference. That way training is happening here and inference can be happening in the real time here so that we can save some time. So then, yeah, I think this is the near-arteric where we can typically do the inferencing and where for doing the QoS management, connection management, radio resource management, interference management, we use something called, I don't know whether it is mentioned here, we use something called XApps. XApps are nothing but applications that, it could be third-party applications or these are applications that operators themselves can create using the data that they are collected. So use the data that is collected to be able to do intelligent operation on top of that. So all the XApps are part of here. Yes, we already talked about the central unit, so which is typically containing your SDAP layer, your RRC layer, and also your your PDC layer. Then we have DU and CU, which we already have seen. VoCloud already talked about how we can use the virtualization concept to virtualize most of the component except the RF and antenna elements. So these are the interfaces. As you see, there are lots of interfaces. Earlier, I was showing you the 5G protocol stacks. There, I was showing you UU interface between the base station and the user, N3, N4, N5. Those are the interfaces. Now, because as you see in the picture, the one that you see, even the green ones, the green label that you see, these are the ones that kind of connecting 3GPP defined components with arterial and non-arterial using A1, E2, and other things. So these are the ones that ORAN Alliance has defined. These are also open and also standardized. So we have different interfaces depending on what kind of data that you wanted to see. Some data can be in the control plane, some data can be in the data plane, some data can be going up, some data can be coming down from these rigs to the respective network components like DU, RU, and other things. So, in summary, the ORAN architecture that I was kind of showing you here, the main object. So, one thing that has to be noted down here is ORAN is not a new technology. It is a new way of deploying the current 3GPP radio access technologies. It started with the 4G. You can deploy 4G as a monolithic base stations, or you can disaggregate by splitting as long as you can able to meet the respective latency and bandwidth requirements. Same thing in the case of the 5G. So that way you can expect the ORAN also playing a big role as we go towards the 6G also. So because we are talking about the deployment methodology rather than coming with a new technology to be able to better serve the users. For that, anyway, 3GPP will look at making 3G as, 6G as the upcoming technology. So because these are the open interfaces where we need not to go to the one vendor to get all the components, hopefully there could be multiple vendors who can do bits and pieces and start selling in the market. Because of more players in the market, the cost may come down. That is one thing. And as I said, we have the rigs, near RT rig and non-RT rig, using which we can able to collect lots of data. These are networks are the one where big data is there every millisecond, granularity event. Many times we don't have the capacity even to store the data, forget about number crunching. So can we do something intelligent so that we can able to better manage the network so that we can, your networks becomes more intelligent, more open, and more self-organizing network. Because as we keep having more and more components, what happens becoming very challenging even for human operators. Can we let network itself understand what is going wrong and do fixing for itself? That's where that comes. And as I said, hopefully this architecture will make cellular networks also somewhat cheaper. So if you look at Wi-Fi, all of you can go and buy Wi-Fi access point and put it because it is hardly cost you 1,000 to 5,000 to 10,000. But you cannot do the same thing here. Of course, spectrum is also one case. But otherwise, the actual cost is kind of like each base station will cost 50 to 60 lakhs. But if you look at here, the data rate that you get, sometimes Wi-Fi will give you much better data rate than. Having said that, Wi-Fi is for indoor and cellular networks meant for outdoor coverage. But thing is, as we go towards 6G, we have to deploy even more number of base stations. But the cost is going more and more. One way to reduce the cost is you have to reduce the cost of per device or per base station. That's where the ORAN comes to the picture. So ideally, we should have this, each house or each building or each office have as dumb entities as possible, like RF entities, and bring all the intelligence to one central office so that we can able to better manage the network. Rather, because we have the active components and the monolithic component at each and every cell site, it becomes too much to deploy, too much to manage. If it is just like dumb device, you don't have to maintain. Like I said, fiber, you deploy and it runs for 10 to 20 years. So can we do certain thing in the case of 5G or tomorrow for 6G, so that cellular networks becomes more and more affordable and also able to provide increasing data rates for emerging applications and use cases. So with this, I stop here, and if there are any questions, maybe I can take one or two questions. On the theory part, we have Dr. Koteshwara is going to give a demo where he will show you the entire stack. Oh, there's a 4:30. Is it? The calendar? It is. That should. Okay. Okay. Oh, yeah, please.
Sorry, I had a question. When you said that there will be multi-vendor deployments with ORAN, doesn't that add another layer of complexity because you have different vendors, but you have to have like an integrated system. So does that add a different layer of challenge?
Yes, yes. What you ask is a really interesting point. That some of the people who are kind of skeptical about ORAN ask you that exact question. Yeah, there are two schools of the thoughts. One is if you disaggregate and have more and more components from more and more vendors, the system integrator has to play a bigger role. If you don't have a good system integrator, even if you have very good component from different vendors, your system may not work. So having said that, if you can able to really address the complexity of managing the network and making sure that they can interoperate, one thing that ORAN is trying to do to make sure that they can interoperate and work well is by making the interfaces open. As long as you and I implement the same interface, so that let's say we are using TCP/IP stack, we say that these two components have to use the same TCP version. So I made sure that my component is compliant to the TCP/IP stack. You also decided to have your component compliant to the TCP/IP stack. As long as both have done using the same underlying interfaces and the standards, they should be able to interoperate. Having said that, yes, there will be a lot of configuration, I think. You'll also see in the case of demo, any misconfiguration here and here, it should not become like one vendor is saying that everything is fine in my system and in your component is failed. I also see that kind of problems going to picture. I think what you have to do is, as I said, you have to make, in the architecture, as you see, if you go back, the service management orchestration framework, NERA-T, non-real-time link. So this is the one that is going to play a very big role. This is where you can actually collect all the data from all the components and you can be able to pinpoint where is the problem. Hopefully, without bringing the human operator, you wanted to let the system self-organizing network. That is the wish, or that is the kind of dream, or the kind of what ORAN is meant for, but we have to see. But yes, that concern is there, and that is one of the active research here. How to make sure that ORAN really delivers as per the promises that is making, without becoming like a caught up in between different vendors saying everybody blaming each other. Yes, that's a good question.
Thank you.
Anyone else? Okay, so good. Anyway, we have another follow-up session where we can see the actual demo, and if there are any questions, we'll have them. Thank you. So, what is it? There's a break now? Or? At 4:30. Okay, so yeah, we'll break for 15 minutes. Thank you.
order to experiment the ORAN platforms. Not only ORAN platforms, but how to integrate the existing other open source mobile stack with the ORAN, which is stated on basically on the NIRA-TERIC and NANA-TERIC. Okay, this is the gives a glimpse, and we see what are the consortiums are available on open source platforms where anyone can do the experimentations. The ORAN-SC is the software community which compared to the ORAN Alliance is a all body of the people, includes SMEs, operators and OEMs, all of them. But there is a separate division of branch called a ORAN-SC, which is a software community. ORAN software community is the one which contributes basically the open source code for different components in the stack. Okay, then basically the ORAN software community is formed between the ORAN Alliance and the Linux Foundation. Who maintains because someone has to maintain your open source code and day-to-day updates and maintain the whatever the Git or any source that is available more efficiently. That is currently, it was not initially, but recently the Linux Foundation has started with ORAN software community in order to maintain the software. Each release that comes from the ORAN software community. Who contributes is most of the operators and also most of the companies that works on like Samsung and all, even Wipro or Infosys, like a lot of bodies are there which contributes the open source code to the open source ORAN software community. That where you see here, basically the ORAN software community which provides the code, which is an integration between the Alliance and the Linux Foundation. This is the wiki page of the ORAN software community where you can get all the wiki page and also the mailing list. If you want to have some issues, you can drop the mail, and also the source code and their little presentation on what they are contributing. You can also see there. Then the current stable release is J, but the current release is the L because it starts from A, B, C, D, then F, I, J, K, L. L is the current version of the release, but the stable release which shows here the J release. Then this is also ORAN software community brings together 3GPP as well as the ORAN, where the basically 3GPP and Linux Foundation together because to maintain the code. Okay, this 3GPP because whatever you build, NANA-TERIC or NIRA-TERIC has to communicate with the 3GPP F1 interface F1C. That's where there is the communication. They come together because whoever implements, they also has to test and evaluate the platforms. Then what is the major focus on the ORAN software community currently is, you could see here the current focus mainly on the non-real-time RIC and near real-time RIC, which are the XApps. They have some XApps that are developed under the ORAN software community, which you can, it's an open source, everything is open source here. There is nothing like proprietary, you can download from the source code and try to experiment it. Then they also have the E2 interface, whatever the interfaces that you define, you have everything. O1 interface which connects both NIRA-TERIC and also NANA-TERIC. Then major is the E2 interface, which today we are going to see how we are putting the parameters in the configuration file and how like OCU and ODU are connecting to the E2 interface. In the configuration file we can see. Now the major contribution comes from the ORAN software community, all these components. Then these are all other, because ODU, ORU and OCU are yet to be come from the ORAN software community. But there is nothing stop you to experiment because there are other software community which provides these components. You can use the, all ORAN, ODU, ORU, OCU and use the other software community and integrate with ORAN software community. There is nothing stops. That's why they are not major focus on this one as of now, but there will be a future which only open DU and open CU that will be comes from the ORAN Alliance. Let's consider this is the a stack for us now and today's demonstration, And we can see, because you have a UE and DU and CU central unit, and you have all the hierarchic and as well as the non-hierarchic. Then we will see here what are the combinations that are available in order to make the experimentations. Like as an open source users, then we would see like if some of my lower layer components are not working, this one, for one of the reason, maybe I can jump to another open source provider who are giving, then I can directly integrate with the hierarchic and non-hierarchic. Like that, what are the mix and match is available. One of the mix is basically you can use the SRS RAN, which is also an open source consortium which provides all the components as a open source. If you have a software defined radio, you can use the UHD drivers and do the experimentation. If you don't have also, you don't need to worry, because you can still experiment by using the emulation with an Ethernet interfaces. Okay, then you can use the SRS RAN project for deploying all these three components, then make them integrate with the ORAN software community, which is provided by non-hierarchic and hierarchic. Okay, this is one combination where you have a SRS RAN project, all the below components, and the upper RAN intelligent controller components from the ORAN software community. The other combination is you can still use the SRS RAN project. Instead of using the ORAN software community, there is another software, open source software, that is called a FlexRig, which comes from the 5G Mosaic project. Then that also you can use, which inbuilt it has the hierarchic interface and also some of the very good features in the RAN intelligent controller. Okay, that nothing stops you. You can use, instead of using also the software community, you can exploit the FlexRig, is another open source again, and use the SRS RAN project, and you can build some apps by yourself and try to demonstrate. The other section is, rather than you have the SRS RAN project, you can still use another open source which is called the Open Air Interface. Again, it is open source. Then you can connect with the ORAN software community for hierarchy and non-hierarchic. Okay, this is another combination. Then the fourth and final combination is you can still use the Open Air Interface and you can connect the FlexRig and Mosaic. These are the four different combinations to make the open source RAN stack with the hierarchy and non-hierarchy combinations. Any of them, they seamlessly works. And some of the links which were the Mosaic we have put here, but anyway we will release most of whatever we are talking here in a GitHub link where all containers, everything that we push, and you can experiment in the labs. Make it more easier basically. Then just to see how the interaction will happen, basically you will have a core network that is for this demo we are using the Open5GS, is again open source core network, but there are so many other core networks are there. For example, there is a Free 5G, is another open source core network, and also there is a Open Air Interface core network, which is again the open source. Okay. Then there are even other open source which is from Fraunhofer. There is their own open source core network is also. Depends on what kind of functionality. Some doesn't have a slice SSNF slice network function. Maybe some has a slice network functions. Like that, different open source give you different additional features that we look for, whichever what we want to look for, then we can use them. Then what is the combination of the experiments basically here? We first deploy the open source core network, which is Open5GS, and then we start deploying the central unit. Whenever the central unit connect with Open5GS, basically we use the command called, you have a configuration file where you define like from whom to whom we are communicating, which is an Ethernet based, like simply an IPs will be there inside and nothing much. There is no confusion because a simple IP, this from CU IP to the core network IP, how we configure. Then next slides I will show how the configuration is performed. Then you have the simple command to run like srscu, and C means a configuration file, and you are inputting the configuration file to the command. then this will connect with the core network. Once it is connect the core network, how do we know that it is successfully connected or not? Hence we should go back to the logs and check if it is connected successfully or not. Then that we will see. Now it shows basically whenever the central unit connected to the core network, it says that number of G node is a 1, which is 1 CU is connected to the core network. On the core network side, we can see that log. What happens in the central unit side? You can see some kind of message which is connection to AMF, which means any kind of open source for the central unit, it not directly connect to the AMF. Okay, access and mobility function. Access and mobility function is the point of contact from the central unit or an aggregated GNB to the core network is always an AMF. We look for an AMF to connect the central unit. That's where it is written AMF. Then it shows the address of the AMF, IP address of the AMF and particular port. Okay, that says it is completed, means which is successfully connected to the core network. Then it shows also what is this, which IP through it is connected to the AMF, because you should have a same subnet, then it can connect to the AMF. Then it also shows the CU is started. Okay, then if any other functions you want to see, you can type H, then there are some commands which comes. But then how do we identify in a successful running of the core network and a successful running of the central unit? By checking the logs of both the components, and we confirm that they are successfully connected. Then once the CU is connected to the core network, then we start running the distribution unit. Okay, once the distribution unit connects, then connecting with the CU, because you always connect the DU with the CU. Now central unit should have an IP mapping of, by knowing one interface towards to the core network, another interface towards to the distribution unit. Okay, that is where we define means, which means technically central unit should have two different interfaces of two different subnets. One subnet connects towards to the distribution unit, another subnet connects towards to the AMF. Then once you connect, then go into the DU logs and check if then the DU is successfully connected. Then it shows what is the available radio type that we have. Then we say it is you have different types. Then normally we use here an Ethernet based, that is where the media of JNQ. There is a kind of drivers that we use to connect both the components. Then it also shows on which local IP, which is the interface used to connect from DU to the CU. Then it shows that DU is started, which means that DU is successfully able to launch and able to connect with the central unit. Then finally you have the UE. UE connects directly with the DU. Okay, you launch the command simple SRS UU and C configuration file. Okay, configuration can be in two forms. One is some cases it will be in the YAML file, some cases it will be in the .conf file. But the structure of the conf files is very same, but only dot format is different, but parameters and notations and everything is same. Then you have connected, whenever user will be trying to connect to the base station, which doesn't mean it is directly getting the data. It will create a GTP tunnel between the UE and the core network. That is when the user is connected to the DU, which indirectly connected to the core network. Mean if I want to check my UE is successfully connected to the network or not, means I have to look for the logs of core network. Means then it shows me how many number of user elements are attached to the core network. That will show in the log. Once I confirm that there are 2 users or 3 users or 4 users are connected, then I know that like users are successfully authenticated and connected to the core network. Now here, then you can see at the core network side this kind of log, which basically says UE initiated a message, and then it says the registration is requested because it is requesting the user authentication to the core network. Once the registration is successful, then it says registration is completed, and it give you how many number of AMS sessions are created. Okay, that is one AMF session is created. Now on the UV side, to check that UV is successfully connected, it should create the packet data unit session, because user has to send a data which need to indirectly has to create a GDP tunnel. On backend, the GDP tunnel is called a PDU session. That is a packet data unit session. Then here you have a random access transmission, random access complete, and RRC radio resource controller connected. And then once as soon as the RRC is connected, then it will establish the end-to-end GDP tunnel, which is a PDU session. That is called a packet data unit session, and it also tells what is my IP address of the UE. If you launch based on that subnet, you will be assigning an IP address. As simple as that. This is the overall, because when you launch the setup component by component, then we can check where the issues are coming. If the suppose you launch the Open 5Gs core network, if it is not working, then you can directly go into the AMF log and see what is the issue. Okay, maybe if I give a wrong IP address subnet which is not existing in the core network, suppose, then it will throw the exceptions. Then each component, AMF, SMF, UPF, every component has a logs. Then we can simply go into Docker logs, Open5gs AMFD, which is the daemon which runs on the backend. You can check the log of it. Same like UPFD, you can check SMFD. You can check all the components logs and see if any issue is there. Hope this is clear. If this is clear, I move to next. If any questions, just interrupt me, please. Then what we would say here, basically all these components are running with the Docker, because which was already pre-installed and created build images. Then we just invoke those images for the demo at least. Okay. Then as I said now, because each one from the CU to DU, we are using the configuration file. From the DU to UE, we are using the configuration file. From the UE to DU, we are using the configuration file. Just in a high level, I will go through because most of the mistakes, whoever start learning the deployments, they make the mistakes in the configuration files. That only leads because we don't properly understand where the IPs has to be, which IP has to put where. If we know that, most of the things will go very smooth. Most of the time we keep around looking on the IP allocation from the component. Just for that reason, I just go through the very brief of the configuration files. Not much, because this is the CU configuration file. It shows you, because as a decoupled CU, or we call it the CUPS, control and user plane separation. Whenever you have a control and user plane separation, then you have a central unit user plane as well as central unit control plane. Both will be there. Then here it shows the control unit, central unit control plane, because all the session initiations happens through control plane. Okay, that is where we first look into the control plane. Then there is a first address that comes, which is the AMF as a subsection. Okay, in the AMF it says the address, because CU has to connect to the AMF. I have to just put the address of the AMF. Whatever the address I am allocating to the AMF, I just put it here. Then it will give me the AMF address, allows me from the CU to connect to the AMF. Then you not only telling that towards the which IP AMF, but you also have to tell from local interface which interface is driving this traffic, because I should have the same subnet, like 10.53.1 is my subnet. Similarly, of this AMF address, then in the local machine, which local container whatever, you have 10.53.1, which is the local interface. This local interface of CU is driving the AMF traffic towards the AMF. That is the IP which we set here, the bind address, and some particular whatever the port that you specify, it doesn't matter much. And then the other important is tracking area code, because that is where you depend your PLMN and also mobile network code as well as mobile country code. Now those two things we PLMN contain both the things. One is called first 3 digits tells us mobile network code, and next 2 digits tell the mobile country code. Just those things, and the tracking area code is the what we specify. Now you see one interesting part is here, right? SST and SSD. There are 2 components are there. One is the slice type and the slice description. There are 2 things. Normally it says, as we have only single slice currently established, then SSD is 1. If not, you want to add more, you can add SSD2, SSD3, SSD4. Then it will create a 4 different slices. Then the F1 AP, this local IP, which we, because this is there are different kind of protocols. This F1 has a one of the protocol, access protocol that you have, application protocol normally. It will bind to the traffic that need to be. This is local interface that you specify. I will go through the next. Then you have the CUUB user plane and the local interface that is binding to the, because the same node can act as a U plane also. That's why you have a one subnet. Now what we see, one interface which towards it goes to the AMF, and the CU also contains one interface towards to the DU interface. When we see the DU, then if the F1 AP interface, because that what interface we call, right, between the DUCE is a F1 protocol, the F1 interface. That is where through this interface 10.53.10.1 is the interface that allows us to connect towards to the DU. One towards to the AMF core network and one towards to the DU. Then in addition to these things, then we have also some more the metrics that we collect from the CU. If you want to collect from the PDCP information and all, we can use them. Then in the DU, you can see the CUCP address I showed, right, 10.53.10.1, which binds basically. Then here the DU which connects to the CUCP, and the byte address is the same subnet in the DU which drives the traffic towards to the CU. Then you have the SDR configuration. You can use one with a JMQ driver, simple Ethernet kind of traffic that goes. There are 2 things we observe here in the ARCs basically. Here you have a 2 IPs and some particular TX port and RX port. The TX port means the DU that is transmitting the data. RX port means it is receiving from the UE. That is where it comes. Now you can see 1.51. When I go into the UE configuration file, you will see the same IP. Here basically what we say that because we are emulating the system, then the DU sends its traffic to the particular IP and the port associated, and the UE is transmitting their traffic to the particular port and the IP. Then the DU goes to the RX port to the of that network and get the data which is transmitted by the UE. If you don't have ZMQ, if you have a software defined radio, you can simply use the device drivers is equal to UHD, and which type of, it is a X210, B210, X410, depending on which software defined radio you have, you can point it out that. Then you configure the number of received frames and the transmission frames. Then the other parameters here, just in the DU we configure basically what is the channel bandwidth, which is a 20 MHz channel bandwidth, and also we define the tag and which band it belongs to, band 3, band 78 or band 48, whatever the bands you define. Okay, those are the cell configurations that comes here. The other is like the DU basically export the metrics, whatever the DU collects from the UE, all the information is exported to the metrics dumper, whatever we are collecting the metrics. I will go through later in the metrics. Then you have the UE configuration file, basically as I said previously. Then the UE I put the TX port of this one, and the RX port will be the DU IP and the respective port number. Then we say same configuration which band that is connecting and what is the PRBs that is allocated is a 20 MHz. Then you have a 106 PRB. Then it is an UE, and UE should provide the the OPC and K, IMSI and IVI numbers, which is standard by each SIM card that you have. All these details are available in the SIM card. Then you have the NAS, because these are the things that you can see in the core network, because NAS is the one is like an access point that you can define, which is the ABN is the access point name, which is the access point name that your phone should display, like whatever IITDH something, then it will display if you connect with the same SIM card and put it in your mobile, then it will show you the SRS ABN, which is just we are using the SRS RAM. Then you have the gateway, just because in order to communicate between the UE and the core network, we need to create one virtual interface. That is, we created by using the we create by using the simple virtual interface, which is a NetEnse namespace, which creates the virtual interface. Through that virtual interface, we can communicate with the core network. This is the first demo that we will go. Basically, you will have a AMF, all core network that we install, and we show the logs of it, how it is active or not. Then we will run the SRS-EU 1 and the SRS-DU and SRS-UE, and we show the matrix is a simple container which contains three components in between, because in the configuration files there is a JSON exporting. We export the whatever the data that is there in the components, we export them, then there should be a collector. Then the matrix will collect the whatever the JSON file, JSON data that comes, and it passes to the InfluxDB. What database we are using for collecting is the InfluxDB. Then the matrix contains inside is the InfluxDB database that stores. Then what Grafana does basically, it fetches the database from the InfluxDB inside the matrix. That is the simple. Okay. Then we show them on the GUI part how these are able to connect and doing some random traffic generation with IPF SIM tool. Then we can show that how the data are visible. Then you can launch as many number of components. We will see launching of 2 of them or 3 of them. You can, there is no limit you can do. This is one setup that you can consider, but there is not required all the CUs, but all the number of DUs can connect to the single CU also. Okay, there is no limit on that. Then we even OpenAir interface also we did that. More number of DUs and single CU with multiple number of 64 UUs can connect in the experimentation. Just for this is an evaluation purpose we are showing. The other setup is, now you see the custom made matrix basically in the previous slide. What you see is not the ORAN, but you are seeing a simple matrix server which we deploy, and it collects from the other all the RAN components. But as a ORAN, we should be more towards the ORAN implementation. That is where we see here. Okay, rather than you use the matrix and Grafana, rather we simply deploy the hierarchy of ORAN software community provided, and we try to launch the XApp. XApp will, what is an XApp? It's a simple key performance indicator of monitoring. What are the key performance indicators? Is the uplink and downlink of the UE. If UE is sending like 10 megabit per second, you should be able to, like there are 10 UEs of them, 10 into 10, which is a 100, suppose 100 megabit per second should be seen in the your XApp. Okay, that is where you have the XApp KPI mon XApp currently has a UE uplink and UE downlink throughput estimation. You can add more number of parameters in the same XApp also. Currently 2 of them enabled, that we show now for the demo purpose. Okay, these are the 2 demo, and yeah, we go for the proper demo on the thing. We will start from the setup 1, and here you go. First we launch the OpenAir interface, Open 5GS. You can start the Open 5GS. In order to check the logs, we use the Docker logs and the name of the container. Okay, instead of giving also that one, you can simply use. Then again do it one more. You log it again. Yeah. Now this is the, how do you check the logs? Now you can't see anything that G0 B1 is associated because we still didn't launch the central unit. Now you will launch the central unit, but if any issues are there, you can check in the log. Currently there are no issues, everything is info, just for information purpose. If there is, you can see the error or a warning, that those kind of logs can be displayed. Can you use the command? Show me the command. Just cat it. Yeah. Yeah, just to explain the command how it is. This is a simple Docker container, and as I described the conf file, which we normally pass to the container. And one more thing is basically important is the, while launching the container itself, you are assigning the IP address to the container. That is where, because it's in the previously in the conf file, cu conf file, I already defined the IP address. That is where we use the simple net. Then this is the interface that is created virtually, and then the container, which is the cu container, will be assigned with an IP of 10.53.1.240, which is defined already in the cu.conf file. Okay, that is where to launch. You can launch. Then, as I said it previously explained, then you have the N2 interface, which is N2 means AMF, N3 means UPF. Okay, simplest thing. N2 interface means it is connected successfully to the AMF. Then you have a FNC because we launched the CU is a control plane. Basically, the control plane information we are showing and showing that it is successfully connected with the local IP and the port number of the local, which we use it sending the AMF address. Then it shows the CU is started. Then once CU is started, then we launch the distribution unit and show that the logs are fine. You can show the core network log once. On the terminal. Open 5GS, yeah. Now you see here, the number of GNBs are connected is 1 because you launched the CU, then it is connected to the core network. Now you launch this DU. We build all scripts also because it will be pushed everything into the GitHub. You can simply run the enter button by using the shell files. Just we want to show the commands, that's where we are putting in. Same for the DU also, we have assigned the pre-IP which is already defined in the du.conf file. You can run. Okay, then you can see the available ones. Then once it is connected, then you have F1C which is connected through the interface to the CU. Then once the DU is started, then it shows that DU successfully is connected. Otherwise, you will see the error logs. Can you run the UV? Yeah, same for the IP also here and the UV log that you pass. Nothing else. Yeah. Then is the things that comes. What is your TX port, RX port, whatever I explained in the conf file, those information, and see here. Once it is successfully connected, then it shows the establishment and what is the UV IP address, which is 10.45.1.2. Then you have the RAN configuration is successful. Then what we see, let's go and check in the core network if it shows the number of UEs connected or not. Yep. Can you do again? Yeah, added number of UPF sessions, and can you go down? Do it again. No, do it again. Just rerun the document. Here, the number of UPF sessions is allocated 1. It should also show the number of UEs, which is equivalent to the UE assigned. And also it tells you log in the, which because SMF does the IP address allocation. You will see right here, DNN is SRS APN, and what is the IP assigned to the user. You can also observe that in the core network basically. The user side, which is the PDU session when it is created, then it is showing you IP, right? How IP is assigned from the core network that you can see in the session. Because basically in the SMF session it assigns the IP address. You can run, open the matrix type. Now we are just running the Grafana to show that dashboard, how many number of views and DUs, and then the traffic that flows. You can start transmitting. This shows we have not started any traffic generation. As soon as we do the hyperf, then you will see all the data comes. You send the hyperf data. Then automatically you will see monitoring the Grafana once we start creating the traffic between the UE as well as from the UPF. This is a small script created to generate the hyperf inside and the random traffic. There is no constant traffic, it just periodically sends some traffic. Here script is there. Now this is sending the traffics. The UE is sending 10.45.1.1, which is the UPF address in the core network. Then 10.45.1.2 is the new UE that we created. Then the UE is sending the random traffic to the UPF, that is .1.1. Yeah, now you can show that. Refresh it. What's happening? You relaunch the other ones. Relaunch it. Huh? Yeah. Whenever when the UE also goes release in between, sometimes it happens, then it is not indirectly not connected, then that is the data is not flowing it. Then because it's not purely stable things, sometimes it happens the RRC release. You just relaunch them, then it will connect. You need to start matrix now, I think, right? relaunching them because the scripts only we just basically the in the structure the matrix server should be because it will show you when you launch first, then you launch the components, then you can see the sequence of them. Okay, that's the reason. Okay, how it is assigned. Can you show me the graph on it? You can show the graph. Yeah. Now you can see the matrix. Okay, one UV attached, one DU, some MCS information, all that comes here. He is not sending any traffic as of now. That's why you don't see. But once we start bumping the traffic, then you can see the total downlink and uplink rates. You can start sending. Yeah, that is where you can observe, and also the UV ones. And we can launch more number of UVs, and you can see the aggregated data that shows in the year. Because this is just a random traffic generated in the UV, and it can source both uplink and as well as the downlink. Is that clear? You want to launch the other CUDU? Just to show you, we will add one more CU and DU and UE and show you that in the graph. Then it will get a new IP for this because they are running in the backend. We are using for other components for the demo. They are running in the backend. It will create the 10.45.1.3 IP because 2 got for the previous UV. Then you see the number of UVs connected and also the bandwidth that comes. It is again disconnected. Okay. One after the other it is sending the data, that's why you see the fluctuations, but you can see the aggregated traffic. Want to show them again. And the traffic that goes on the both sides. Okay. Like that you can launch a number of DUs, but you can also use single UV and aggregated DUs and aggregated UVs. There is nothing stops. Yeah. You can stress as much as possible and see how stable they are, because you can run more number of UVs, 10, 15, and see how they are able to connect them. You can do all the experiments. Now we clean it up this one and go for the second demo where we are launching the NIRATIC and the XApps demo. You can clean. We will push everything into GitHub and send the link. If in case delay, you can drop a mail. Then we will send the link with all the tools, pre-configured conf files, and also the pre-configured images and everything. We clean the previous code network and again launching the new one. Yeah, okay, one second. Can you open the conf file, please? Of this one. Conf file. I want to show the E2 section where we define. Yeah. That is in the ZMQ.CU.YAML. Just to show you the interface, because previously you have the matrix, then you define the IP of the matrix. Similarly here it connects through E2 interface, right? CU and DU are connected through E2 interface. That U2 interface we will also put in the configuration file, which I didn't explain in the previous configuration. Now here, you see here, right? You are saying the E2 is in a configuration file, and both using the control plane data as well as the user plane data, that is true, and also is a KPM enabled because you are monitoring the KPM from the XApp. Okay, hierarchy rig, that is where you define the here E2 SM. The SM means service model. E2 service model, which is used for collecting the key performance metrics at the XApp. Okay, that is where you have, and you have the also the other which is RC enabled, and you have the IP address that you are where the rig is running. Then through which interface it is communicating. Always bind address is like a rule of thumb. Bind address means local address. The other address means the remote address. The bind address is the channel that pass your data to the remote address. Means hierarchy first should be launched, then the other components should follow them. Now CU is running. Then you can show the rig log if you want. Then each time you launch that CU, and in the rig log you can see that attachments. The CU attached to the controller and the DU attached to the controller. Like that you can see each of them. Yeah. These are the logs. Which node is attached to what? Like we can see them. Tells you that the addresses which are attached. Go ahead. Right. Trick. Yeah. They all are very simple shell files. That's easy for you also. Just tracking enter. Okay. Then once it is also launched, then it also connects the another one. You can see all those logs in the hierarchy. As soon as you launch the components, and you can log can be observed in the hierarchy. Yeah. You can launch the UV. Then same procedure, it gets the PDU session and gets the IP address. Then you launch the except you already launched it. Launch the except. Pin also. Do either. You transmit the data and also launch the XApp, because XApp will give you the bandwidth, or you launch first XApp and then launch the DU and start transmitting the data. KPM on XApp. Yeah. Now you see the 1 KB. So the values that you see here is the uplink throughput, UE throughput downlink, and UE throughput uplink. And the information in the brackets notifies us the basically how many number of kilobits per second that we are transmitting. It is simply transmitting the simple pin. Can you add minuses? Then you can say like 512 bytes. Then it should show you around 512 bytes, 512 into 8, which is a 4 kilobits per second. Then the number it should show us is the 4. Yeah. Okay. That's like that. You can do the packet size increasing, and you can also see what is the data uplink and throughput that is transmitting. Like that you can, or you can also start doing the IPF and everything will do it here. You can increase the packet size to 10,000, or at least, yeah, or then 10,000 into 8, you can say 80 kilobits per second. Okay, like that you can, the XApp now, previously you were monitoring through the metric, now you are using a simple XApp which it simply collects from the DU and it tell you what is the aggregated bandwidth. If I launch 3 UUs and each was sending suppose 10 Mbps, 10 Mbps, then it will be 30 Mbps that you can monitor here, which is 300 kilobits per second. We can monitor that's a 81 and you can see the things. Some additional data that also comes, but you can neglect that. But the 80 came basically because I am sending the 10,000 into 8, which is a 80,000, which is 80 kilobits per second. And one out of for every second that will give you the 8 kilobits per second. Then there is a every 2 seconds. It will, you can define the thresholds. It's not fixed. Currently we put for every 1 second, but you can change it to 4. I don't want every 1 second. I just want every 4 seconds. What is my aggregated data? I simply use that. Out of these things, you see one case 163, which is around aggregated of 2 seconds. Then one is give you the straight way, one give you every 4 seconds or 5 seconds an aggregated value, which is the like 2 of them, 160 kilobits per second. Like that you can transmit as much of the data and then launch the XApp. It will give you the kilobits per second that you transmitted. Then you can build for every other purpose. You want to know DU, suppose what is the CQI, users are roaming around, you want to get their CQIs. Then you build a small XApp, it will go and fetch at the DU and it will give you the XApps, CQI values. Then or you want to allocate the priority the resources, then you forecast the CQI. Once you have the data, huge data, then you forecast the CQI and assign the user earlier. That is the way the inference come into a picture, because once you use an XApp of CQI measurement, it measures the CQI and it also try to forecast you the CQI, and rather than 5 minutes, you take the decision earlier 5 minutes and assign them the required resource blocks. That is the way you can build as many XApps. Here X stands for any. In the non-arteritic we have RApps normally we call. R means RAM, which is mainly used for policy configurations. That is, whereas here X stands for any kind of app. You build whatever the app you want. That's the reason the X stands is a XApp. Any kind of app. Currently we are using the throughput measure or downlink coupling measurements app. Then you can build CQA app, or you can build traffic steering XApp, or you can build any kind of other apps. Okay, that is the thing. Then I can open for the questions. Any questions? I completed even I took 9 minutes delay. Yeah, please.
It's a very nice demo. But generally, what we see, even I am doing all of this setup from the past 6 months, but generally it is not that seamless.
Yeah, because that is where I just see you. Because normally what we are trying to do is a workforce development, because this is a very new technology which may come after 2030 around, right? You need to build a workforce for that. But what we observe, because suppose these two came with a zero knowledge, we took 6 months to train them. That is the way you always have a period. Even my lab also, when I took, they don't know what is a RAM even, but they start doing deployments and learning how logs to be measured and all. There is a cycle of once. The beauty here is once you are in that phase, it is easy. Like once you learn the setup and how to debug it, then you go into deep actually. That is like, it is a workforce development, or you can call it. It has around 4 to 6 months is the quality time they have to spend. It is not that easy, and the open source are not stable, but we will make them stable because we work. That's a reason. Different, you suppose while getting, you get master branch rather than the develop branch, then you are gone. You realize that you get a master branch, then by that time it passes 3 weeks. There is a time that takes, obviously.
Yes, one more doubt is here we have the rig from the Oran SC. So the Oran SC uses more of 1,000 piece of lines of code.
Yes.
So like when we have such big code, so how should we debug? Like if any warnings, how shall we debug considering the case that we are not deploying it in a very base system? There are other deployments which might be running on some other container runtime or something.
Two things which if you want to get into hands-on basically, even for me also, when I deploy, I'm also still I learn every day. One thing is just follow the forums. I very closely and you will get onto the track. This is what I normally follow all the time because I follow strictly the mailing list because I don't get it. If I miss some days, it will be because some new logs comes, new things, and it will make me little nervous. That's why I closely follow the mailing list. The second is like we deploy and learn the second part. And third, we also look into the standards. Okay, well, this suppose at least in the ORAN case, ORAN software community, whatever it is doing, it mostly based on their latest standards. Okay, if you follow their latest standards, then also helps us on what is the, because you don't know suddenly some work packages start pushing some code. This code related to which one? What is the purpose of it? Then this is practically associated with some of the standard that is defined. Reading the standard and following the mailing list and doing our own hands-on and get ready. There is a time consuming. There is no like there is nothing like that. I'm pretty. Even if you spend 2 years on the same code and same things, then it is quite difficult. Sometimes suddenly error pops up. The other best practice I do, like suppose we resolve all the issues. We are at least in the phase of demonstration, right? Now we will keep without failing anything. We should maintain our own local repository. If not, then tomorrow they will simply push from like 22.04 to 24.04. You are gone basically. That is the reason anything, it's a small demo you are able to there. Better you keep your repository. Even after 3 years, you can have the same deployment in the same at least restricted configuration. I have the same environment, then I can at least deploy that. That's the best practice is keep whatever the working in your local repository, maintain very efficiently that one. Even small changes are done, we simply push. In that way, at least we will be saved for something.
Thank you.
Thank you so much. Any other questions?
Sir, did you get a chance to explore more on XApps?
Yes, that's what we are working on. There are DApps also we are working.
Okay.
One for the DApp for changing the resource blocks because then depending on the use case, you change from the round robin to fair scheduling algorithms and all. There are small DApps that we are working on. And the XApps basically CQA measurement and also those XApps that we are focusing because in order to take the decisions. Some intruder detection, some reliability XApps also in the pipeline, which we will see in the, because more interestingly actually we want to push all these logs to an LLM, let the LLM learn, then we take the output of the LLM and automate as much as possible. And that is the also in the next, we were trying to get all these logs and push to a simple LLM model. Then see, whenever the issue is there, then LLM tells me that where is the issue. then we go and fix it.
And I see, like, I worked like 6 months back or something. So I saw 2 exams given by the Mossack 5G. One is RAM slicing, one is TC. I'm not sure if it is traffic classification.
Yes.
So can you?
Yeah, we have some publication on the same except that I recently done. Okay, for me I use FlexRAM, FlexRig, and also OpenSC. All of them mix and match whatever the 4, one way or other we have some publication on 4 matchings. Yeah, FlexRig also very much confident. We change the PRB allocations with the FlexRig and all those things. Yeah. Thanks. Okay. Thank you so much and have a nice evening. So thanks to both of them. Yeah, they spent their blood here. Yeah, come to here. Yeah. Good, come. Yeah. Both of them are struggled for almost 6 months to bring the sunlight environment. Come, go ahead. Yeah, Yashwant and Sonia, thank you so much for the efforts.
Yeah, I think we have to thank Koti for all his right. So he's kind of training another workforce here at IIT Hyderabad. And anyway, we'll put all this on YouTube so that whoever wants they can also join.
This we will put everything is in the GitHub and open source it, then you can experience.
But, so thanks for joining, and I think 6:30 we have cultural sessions in the same room, so we have some time. Thank you. Sonia and Vaishnav.
to showcase the grace, rhythm, and storytelling essence of this vibrant dance form. Let's start with the invocation song, Vatapi Ganapatim Bhaje, dedicated to Lord Ganesha, the remover of obstacles.
वक्रतुण्ड महाकाय सूर्यकोटि समप्रभा निर्विघ्नो कुरु मे देवा सर्वकार्येषु सर्वदा गणपति भजे ओम गणपति भजे ओम गणपति भजे ओम गणपति भजे ओम
That was a vibrant performance. Thank you. Next we have a song Pushpanjali, a heartfelt offering of flowers to the God, teachers and all the audience here.
जन्नत की टता
That was indeed a stunning performance. I'm sure everyone here felt the wave of awe and admiration in the performance. Moving on, we have Kalinga Nartana, a story of Lord Krishna's playful yet powerful dance atop the serpent Kalinga. It was truly a bliss watching Lord Krishna visit our event with us today. Next we have Ksheerabdi Kanyaku, a popular song celebrating goddess Lakshmi's glory.
दीपस्त्वमेव जगतां दयिता रुचिस्ते दीर्घं तमः प्रतिनिवृत्त्यमिदं युवाभ्याम् स्तवोऽव्यं स्तव प्रियमतः शरणोक्तिवश्यम् स्तोतुं नायकः देवानां तुष्टितो दीपः पितॄणां प्रीतिदायकः दीपज्योतिः दीपज्योतिजनार्दनः दीपो हरतु मे पापम् सन्ध्यादीप नमोऽस्तु ते सन्ध्यादीप नमोऽस्तु ते सन्ध्यादीप नमोऽस्तु ते या स्त्री पतिव्रता लोके गृहे दीपं तु पूरयेत् दीपप्रदक्षिणं कुर्यात् सा भवेत् मयि सुमङ्गला सा भवेत् मयि सुमङ्गला सा भवेत् मयि सुमङ्गला जगति अलवे मंग
Truly enchanting, isn't it? Finally, prepare to be amazed by the plate and pot song performance. This is hallmark of Kuchipudi dance tradition and a true testament to skill, balance and artistry. I'm sure everyone here would agree that it was worth the wait. Let's give a huge round of applause for these young talents. Through their graceful moments and intricate storytelling, they have brought to life the essence of Indian culture. A heartfelt thanks to Dr. Vijay Lakshmi Harikumar for her dedication for preserving and promoting this beautiful art form. Ma'am, can you please come on to the stage along with the group? Now I request Dr. Anthony Franklin, sir, Head of Computer Science Department, to come on to the dais and felicitate Vijay Lakshmi ma'am and her group.
నువ్వు ఫోటో తీసుకొని జరుగు ఫస్ట్ ఫోటో తీసుకొని జరుగు అందులో 2.8 తీసేసారు 2.8 సైడ్కి రా ఆగు జస్ట్ వెయిట్ ఆగరా ఓకే సార్ డన్
Thank you, sir. Thank you, ma'am, for making us this wonderful performance. Stay tuned as we are going to continue to celebrate the diversity of performances in today's event. Next we have an astonishing Bharatanatyam performance by Adhirath Jyotika Meenakshi Shivalasya from our very own IITH Dance Crew Shuffles Classical Wing Talkaran. Please welcome them with an applause. exhibition of exceptional artistry. Now we have a captivating Mohiniyattam performance by Megha, bringing to the life a tale from Bhagavata Purana. Good evening, everyone. Next is a Mohiniyattam performance. Mohiniyattam is Kerala's classical dance form, celebrated for its fluid movements and evocative expressions. Tonight, we delve into a timeless tale from Bhagavata Purana, a story that embodies devotion, redemption, and the boundless grace of Lord Krishna. This performance brings to life the encounter between infant Krishna and Pudana, a demoness sent by the tyrannical king Kamsa. Kamsa, fearing the prophecy that Devaki's eighth child would end his reign, sought to eliminate every child born to her. Yet, Krishna, the divine child, was miraculously saved. Kamsa dispatched Pudana, disguised as a beautiful woman, to carry out his sinister plan. She found the infant Krishna and, despite her malicious intent, was moved by his divine presence. Her maternal instincts surfaced, but fear of Kamsa compelled her to proceed with her mission. Pudana offered her poisoned milk to Krishna, but the Lord, in his infinite power and compassion, absorbed not only the poison, but also her life force. In her final moments, Krishna revealed his cosmic form to her, granting her moksha, a liberation reserved for the blessed. This act of grace stemmed from Pudana's past life, where she had longed to nurse Lord Vishnu in his Vaman avatar. Through this divine encounter, Krishna fulfilled her wish, turning what seemed like an act of malice into an act of redemption. Through the flowing elegance of Mohiniyattam, I bring to you this poignant tale of love, transformation, and divine compassion. Allow the graceful movements, rhythmic patterns, and the expressive storytelling to immerse you in this extraordinary narrative of Krishna and Pudana, composed in Raga Kapi in Adital. Let us embark on this journey together. Sit back and enjoy the performance.
कंसशासनम् आकर्ण्य मम हृदयम् शीलं कर्णवेदिया कंसशासनम् आकर्ण्य मम हृदयम् शीलं कंसशासनम् आकर्ण्य मम हृदयम् शीलं कर्णवेदिया कंसशासनम् आकर्ण्य मम हृदयम् शीलं शासनम् आकर्ण्य मम हृदयम् मम हृदयं श्रीधीरं कर्णवेदिनां सशासनम् आकर्ण्य मम हृदयं श्रीधीरं कर्णवेदिनां सशासनम् आकर्ण्य मम हृदयं श्रीधीरं कर्णवेदिनां सशासनम् आकर्ण्य मम हृदयं श्रीधीरं पूर्वकाममी पूर्वमानसये सुहृदवतीयाय माध्यता पूर्वकाममी पूर्वमानसये सुहृदवतीयाय माध्यता सुहृदवतीयाय माध्यता पूर्वकाममी पूर्वमानसये 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 सुहृदवतीयाय माध्यता पशुपतेः नरुपार्पुञ्जिरी पूषयीवतु परमात्मा पशुपतेः नरुपार्पुञ्जिरी पूषयीवतु परमात्मा शासनम् आकर्ण्य
Thank you, Megha, for your splendid performance. Megha has portrayed this timeless tale of divine compassion and transformation, leaving us awestruck. Truly, when it comes to dance forms, language is never a barrier, and communication in the network is absolutely divine. With this note, I would like to thank all the performers and audience gathered here to witness this amazing event. And thank you, everyone. We have dinner planned. We have a welcome dinner in the guest house, 4th floor. We'd like to meet together and have more discussions there. Thank you.
Wait. One more.
Wait.
Amma, one more pose. Anna live చేస్తున్నా.